Hi students, today we are going to discuss a new topic, namely spring mass pulley system. So I can see the diagrammatic representation. It consists of a spring whose spring constant is K, and a mass M is attached to the free end of a string which is passed over a pulley. Now the system is in equilibrium. It is at rest initially. So now this mass will have some weight which is acting in the vertically downward direction. Because of that weight, there will be a tension in the string. Since the string is continuous, the same tension will be observed on the left end of the string. So T is the tension which is acting on the string on both sides. Now initially the mass is at rest. Now I am going to pull the mass in the downward direction. See here, this mass is pulled down through a distance x. So as a result, initially it was at rest. So it was at rest. Initial velocity was 0. Now when I pull this in the downward direction, it will move with a velocity v. So it is gaining an acceleration. So downward it is moving, it is gaining a velocity v. So in the downward direction it will have an acceleration a. Okay. So that the tension in the string T must be equal to the mass of the block into its acceleration. This is the first equation of understanding. Okay. After pulling the mass, if I will leave it, what is going to happen? Again it will go up and the spring will be again compressed, then extended. Alternately it will be oscillating simple harmonically, and there is a certain period of oscillation for this spring mass system. So we want to derive an expression for the period of oscillation of the spring mass system in this case. Okay, so let us start with the equation. The tension T is equal to mass into acceleration. Okay. Now, on the left arm, there is the same tension is acting on the string. So, on the left arm, the equation for the tension must be equal to minus of K times its displacement x1. The spring will be displaced in the upward direction. So, there is a minus sign and x1 is the displacement produced in the spring. But can you see that the bottom end of the spring is also fixed? And the pulley is also fixed, and the one and only movement is that of the mass. Therefore, in this case, when we pull the mass downward through a distance x, the spring also will extend through the same distance x only. So, in this case, x1 must be equal to x, and not in all the cases. Only in this example, the displacement x in the downward direction will be equal to the displacement x1 produced in the spring in the upward direction. So I can also write T is equal to minus of K times x. Why? Because in this case x1 is also equal to x. Okay. So now you can see T is equal to M into A on the right arm of the string, and T is equal to minus K times x on the left arm of the string. I am going to equate these two and get an expression for acceleration. So equating these two, MA is equal to minus K into x, or acceleration A is equal to minus K by M into x. So this is the equation for the acceleration of the mass or spring mass system. Okay. Now what is going to happen? I told you, when you pull the mass and release, it is going to oscillate simple harmonically. So by the definition of simple harmonic motion, from definition of SHM, okay. So, from a definition of a simple harmonic motion, the acceleration also is equal to minus omega square times the displacement x. Okay. So, omega is called the angular frequency, 2 pi times the natural frequency of the system. So, this is from the definition of SHM. So, I will take this as equation 2. Now, I am going to equate these two. Okay. So minus omega square into x, minus omega square into x will be equal to minus k by m into x. So this is minus k by m into x. So this minus and x get cancelled on both sides. So I get omega square is equal to k by m, and omega is equal to square root of k by m. Okay. So this is the required equation number 3. So what is the period of oscillation we require? Period of oscillation is given by t is equal to 2 pi by omega. T is equal to 2 pi by omega. So this is equal to 2 pi divided by omega is what? Root k by m. Or now I can rewrite this as t equal to 2 pi into square root of m divided by k. And this is the required equation number 4. So we have derived an expression for the period of oscillation of the spring mass system, okay, associated with the pulley. Yes, my dear students, now the same equation can also be derived from the law of conservation of energy also. Understand that? Now you see that when the mass m is pulled downward, it gains kinetic energy, okay, and the spring gains what? Potential energy. So the total energy of the spring mass system, that is the total energy, means what? The kinetic energy plus potential energy remains constant always. So I start with the law of conservation of energy. The total energy, I will take this as what? E total. That is equal to E itself, I will take the symbol, okay. So E must be equal to potential energy plus kinetic energy. So E is equal to potential energy of the spring plus kinetic energy acquired by the mass. Okay. So this is half k x square. This is the potential energy of the spring, and plus the kinetic energy of the mass is half into mv square. Okay. So now here x is a variable. I am pulling the mass downwards from 0 to a few millimeters downwards. So x is a variable, and initial velocity was 0, and finally it has gained a velocity v. So v is also a variable. But left side total energy is not a variable, it is a constant. So if I differentiate left hand side and the right hand side, what will happen? With respect to time, I am going to differentiate on both sides. So dE by dt on the left side must be equal to half k becomes what? K by 2 into 2x into dx by dt plus half m will become what? M by 2 into 2v into dv by dt. Okay. So left hand side dE by dt must be equal to 0 because the energy doesn't change, total energy remains constant. So the differentiation of a constant will be equal to what? 0. And this is equal to what? This 2 and 2 get cancelled. Okay. So this is k into x. So this is k into x into dx by dt is nothing but the velocity v. Understand? Velocity v plus here also 2 and 2 get cancelled. M into v into what is the dv by dt is rate of change of velocity, is it not? So rate of change of velocity is equal to acceleration. Understand? Now I take left hand side 0 minus mva, okay, or I will take mva, okay, mva on one side, the other side will be minus k into x into v. So this v and v get cancelled, therefore acceleration is equal to minus k by m into x. So this is our equation number 5. Okay, acceleration is equal to minus k by m into x. So already we have got equation 1 minus k by m into x. Same expression we are getting here also, is it not? So once again, if I will equate this with minus omega square into x, this becomes the same as the equation 2. Okay. So comparing these two, once again I get what? Once again I get omega is equal to square root of k by m, and t is equal to 2 pi by omega. This is equal to 2 pi divided by square root of k by m, or T is equal to 2 pi into square root of m divided by k. So the same expression we are getting here also. So we have verified from the law of conservation of energy also that the period of oscillation of the spring mass system in this case is equal to T equal to 2 pi into square root of m by k. If you take the reciprocal means you will get the frequency of oscillation also. So what is the frequency is equal to the reciprocal of the period, isn't it? So this must be equal to 1 by 2 pi into square root of k by m. I hope you must have understood well. Fine.